Now, let's look at the last important component of data transformation, feature selection. As the name suggests, feature selection involves choosing the most useful features from a large set to use in a machine learning task. That's why it's also known as dimensionality reduction. It helps reduce the complexity of the dataset. First, let's use a straightforward example to explain why dimensionality reduction is so important. In this case, we're training a model to recognize lighthouses in images. We could feed the model images that have 64 different colors, but each image file is 11 megabytes. If you have a dataset with many lighthouse images and each image is 11 megabytes, the overall dataset would be huge. This would significantly increase both the resource cost and the time required for the machine learning task. However, if we use an image with just 2 colors, the file size drops to 88 kilobytes, and we can still clearly see the lighthouse. In other words, this new data point is still usable for training a model to recognize lighthouses. Of course, we do lose some information in the process, like the lighthouse's color. In some cases, the color might be important, for example, if we're training a model to predict the color of a lighthouse. But for this particular machine learning task, even if we ignore color, the model can still be trained effectively. In practice, the loss of some information is acceptable when you consider the significant resource optimization gained. I believe you now have a pretty intuitive understanding of why dimensionality reduction is important. Now, let's look at the definition of dimensionality reduction. It's the process of transforming high-dimensional data into a lower-dimensional representation while retaining the most important information from the original data. The terms high-dimensional and low-dimensional are easy to understand. The key question is, what do we mean by the most important information? Once we clarify that, we can choose the useful features accordingly. Dimensionality reduction is one of the most common tasks in data preprocessing, and it involves a variety of techniques. Today, we'll just mention 2 common methods, especially principal component analysis, or PCA. Now, let's use a smaller example to understand what we mean by the most important information in a dataset. This time, we'll work with a dataset that has 2 features, the science and humanities scores for 5 students. If we could only choose one feature to predict or classify student performance, we'd want to pick the one that gives us the most clear and consistent information about their abilities. For example, if one subject's scores vary more and better reflect differences in student performance, that might be the better choice. Essentially, we'd choose the feature that seems to carry the most significant signal related to what we're trying to predict. If I have to choose one feature to classify student performance, I would look at which feature shows more spread and distinct differences among students. For example, if you plot both science and humanities scores on a graph with a range from 60 to 100 and find that the science scores are more varied while the humanities scores are clustered tightly together, then science would likely be a better indicator of performance differences. Ultimately, the best feature is the one that carries more variance and clearly distinguishes between students. If you answered that we'd use the science feature, congratulations, you got it right. Your intuition is spot on. We can see that the data points for science are more spread out, making it easier to detect patterns that differentiate students. Although the humanities scores can also be distinguished, their range is smaller than that of the science scores. Since we can only pick one feature, science is the better choice. In fact, this reflects a common real-life scenario, where science scores tend to vary more significantly among students. We can use variance to represent the spread or variability of the feature's values. A higher variance means the values are more spread out across the dataset, while a lower variance indicates that the values are closer to the mean. We already went over how to calculate variance when we discussed the z-score, so I won't repeat that here. Just remember that variance is a crucial concept in machine learning. It appears in almost every topic and algorithm, so you need to fully understand both how to calculate it and what it means in practice. If a feature has very low variance, it might not add much value to classification or regression tasks and could even be removed. For example, house street numbers in a dataset typically show very little variance and are unlikely to be useful when predicting house prices. Similarly, in the example on the slides, lower variance indicates that most students have similar scores in those subjects. On the other hand, Higher variance means that scores differ more among students, which makes that feature better at distinguishing individual performance. We can call the most important information in the data the principal components. In practice, there are different ways to determine the principal components of a dataset, such as by using variance, information entropy, or even specific domain knowledge. We won't go into detail about each concept here, but when we cover related topics later, we'll dive deeper into these ideas. To help reinforce your understanding of principal components, I'll use a photo of myself as an example. If we divide this photo into different regions, which region do you think has a larger variance? As we discussed earlier, variance represents how much the data varies. In this photo, the region with the most noticeable variation is likely where my body meets the background because that's where the colors change dramatically. It's exactly those regions with high variance that the model is meant to identify and use as valuable information. If we compress the photo's dimensionality to an extreme, keeping only to colors, we end up with the image on the far right. Even though this image has lost a lot of specific details about me, like my hair color and skin tone, it can still be used to train a model to recognize me. That's because it still preserves regions with high variance, such as the shapes of my facial features. Similarly, we can further compress the image so that it only retains simple lines. This significantly reduces the complexity of the data point. As you can see, all the background information has been removed, leaving only basic lines that outline my facial features. With the right model and parameters, there's still a chance to use this most simplified version of the image for training. Now, let's look at some methods we can use for dimensionality reduction. First up is the filter method, which is based on mathematics and statistics. For instance, we might divide an image into segments since every pixel has a specific value. We can treat each region as a major feature and calculate its variance. After calculating the variance for each region, we can identify the areas with high variance and use only those regions to train the model. For example, if we decide to use only two components for our machine learning task, we should keep the two highlighted regions shown in the image on the right. Using this math and statistics-based filter method, we don't need extensive machine learning or domain knowledge. We simply follow the variance formula in our code, then systematically search each region and apply the variance calculation. This filter method quickly allows us to discard a lot of unimportant components. This method has clear drawbacks. Regions with high variance might not be suitable for your specific machine learning task. For example, if you're training a model to predict the color of my clothes, then focusing on the region with the highest variance like my face is completely inappropriate. Similarly, this method completely ignores the interactions between different regions. For example, the shape of my head is an important feature, but it relies on the combination of multiple regions. If we only choose the two highlighted regions from the image on the right, we lose the opportunity to capture the head shape feature. Another solution is wrapper methods, where we evaluate subsets of features by training and testing the model with different combinations. This is essentially a trial and error approach. When using this method, we have to consider whether the cost is justified. While wrapper methods can work well for certain tasks, they tend to be quite expensive overall, so we won't delve too deeply into them here. In the upcoming videos, we'll focus on principal component analysis and linear discriminant analysis, which are the key topics for this session. Although the calculations for these methods can be complex, it's crucial that you understand the underlying logic behind them.